Creating rectangles using extraction rules. When we work on creating data search algorithms in the extraction rules activity, we work with rectangles positioned within the Cartesian coordinate system. The Cartesian coordinate system is a mathematical framework for locating points in 2- or 3-dimensional space using numerical coordinates. The key difference between the extraction rules activity coordinate system and the traditional Cartesian coordinate system lies in the direction of the y-axis. In the extraction rules activity, the origin is located at the top left corner of a page. The x-coordinate increases from left to right, while the y-coordinate increases from top to bottom. Distances are measured in dots by default, but you have the flexibility to switch to units such as inches, centimeters, millimeters, and points. Each detected element on a page has its region, which is essentially a rectangle that surrounds the element. Thus, when working with layouts, our primary objective is to find these rectangles. There are several methods to define rectangles. The first method is specifying rectangle coordinates. This involves defining the coordinates of the top left corner, x1, y1, and the bottom right corner, x2, y2. The second method is defining a rectangle by its corner and its dimensions. You can specify the rectangle's top left corner, its width and height. The third method is describing rectangle boundaries. This option is simply another interpretation of the first option. Look here. The x-coordinate of the top left corner corresponds to the left boundary of the rectangle, while the y-coordinate represents the top boundary. Similarly, the coordinates of the bottom right corner define the right and bottom boundaries. When creating layouts, we need to repeat to ourselves these rectangle boundaries like a mantra: left, top, right, bottom. Let's illustrate this with a few examples. Consider a rectangle R1, which could be automatically created around a found text field. In FlexiLayout language syntax, you can define it as follows. Let R1 equal rect with the following coordinates: 200, 300 dots for the upper left corner, and 700, 500 dots for the bottom right corner. Here, the values represent 200, which is the left boundary, 300, the top boundary, 700, signifying the right boundary, and 500, which is our bottom boundary. Now, let's say you want to specify a search area, which always is another rectangle, R2. You can describe it as a rectangle with coordinates 500, 700, 900, 1200 dots. Once again, you can see the boundaries: left, top, right, bottom. But often we don't know the absolute coordinates of elements on each page, especially when their positions vary across different documents. Instead, we define search areas relative to the regions of easy-to-find elements, often referred to as keywords. Let's define the R2 rectangle based on its relation to the region of the already detected R1 rectangle using the rectangle's boundaries. For instance, you can specify the left boundary of the R2 rectangle as equal to the right boundary of the R1 rectangle, expressed as r1.rect.right, minus a certain distance. In our case, it's 200 dots. Similarly, the top boundary of R2 can be calculated as equivalent to the bottom boundary of R1 plus a specified distance. Remember, y-coordinates increase when we search below the keyword. In our case, this is 200 dots. By using this approach, you can define the right boundary of R2 as equal to the right boundary of R1 plus 200 dots, and the bottom boundary of R2 as equal to the bottom boundary of R1 plus 700 dots. At this point, you possess the necessary knowledge to efficiently generate rectangles within the extraction rules activity.